This week is Chemistry Week, and the theme is Chemistry Colors Our World. For our organic chemistry project, we had to pick organic dye molecules. My organic dye molecule was carmesic acid. The molecular formula is C16H10O8. That means there are 16 carbons, 10 hydrogens, and 8 oxygens in the entire molecular structure. There are 3 functional groups in carmesic acid. There are alcohols, ketones, and carboxylic acid. Carmesic acid is a polar molecule, therefore making it soluble in water, because water is polar as well. In nature, carmesic acid is also known as natural red 3, meaning that the color is red. The reason that we can see the red is because of visible light. Visible light is the natural light that our human eyes can see and pick up. Carmesic acid is red because all the other colors of Roy G. Biv, or the rainbow, are absorbed into it, while red is the one that is kicked back or reflected back. In lab, we can test the color or how much light is absorbed or reflected through chromatography. Chromatography literally means color to write. The term is used to separate mixtures. Carmesic acid, since it's red on the visible light spectrum, its wavelength is between 620 and 780 nanometers. Carmesic acid is used in everyday life for brilliant, vibrant scarlet red dye, and also for medications. Some of the medications that it's used for are for treating wounds, ulcers, burns, scars, disorders of the muscular or neuromuscular systems. One in particular is Parkinson's disease. And that is my organic dye molecule, carmesic acid.
My compound is azollitmin, which is a fragment of the litmus molecule. And litmus is probably a familiar term if you're in a chemistry class. It is the compound that is put onto red or blue litmus paper to determine whether a compound is acidic or basic. Azollitmin has a formula of C10H11N3O. The atomic mass of azollitmin is 189 grams per mole. The functional groups are drawn up here in orange. We have an amine and an amide. So as I said, azollitmin is a fragment of litmus. And what litmus does, as I said, allows us to determine whether a solution is acidic or basic. And how that's done is the litmus molecule is actually diprotic, which simply means that it has 2 hydrogens that it would get rid of in a reaction. So when we have red litmus paper, which has the weak diprotic acid, and it reacts with something that is basic, it gives off those 2 hydrogens, and the acid reacts and forms a conjugate base. And those hydrogens react with that conjugate base and turn it blue, which is why we see the red litmus paper turn blue in a basic environment. Now, the simple acid-base reaction can be seen here with sodium hydroxide reacting with hydrochloric acid to produce water, and sodium chloride, which is basic table salt. So the way that acid-base reactions work is we take our base and we can split it down the middle and do same with our acid. So this gives us a cation and an anion here, and a cation here, and an anion here. So what is going on in this reaction is just a simple substitution. We are attaching this anion and this cation, and this cation and this anion, which will give us these products. If we weren't sure whether we had sodium hydroxide or hydrochloric acid, we could test this using our litmus paper. So say we had a sodium hydroxide solution and we had some blue litmus paper. Blue litmus paper is already a basic solution. So if we add sodium hydroxide to an already basic litmus paper, no reaction will occur and no color change will occur. However, if we take the same litmus paper and add HCl, which is acidic, then our blue litmus paper would take the hydrogens from this chlorine in the same manner in this reaction, and our litmus paper would become red, which would prove that we have an acidic solution. Much in the same fashion, if we take our sodium hydroxide and add it to red litmus paper, then our red litmus paper would lose its two hydrogens and turn blue, proving that we have a base.